Hello everyone. In this video we are going to talk about modules briefly. So modules are like libraries of C++. It's a container of code. It's a collection of code, Python code that can have functions, classes, variables, and so on. And it's a code. It can also include runnable code basically. And when you write some of the things, some of the code that you will be using over and over, this and making them a module is gonna make, in general, writing code easier because you write this code one time and you save it as a module, and anytime you need to use the variables, functions, or anything inside this code, all you need to do is to import this module like a library, like a collection of functions, and that's all you need to do. So you say, hey, here I have written something called my calc module, and it has two methods, and so every time I want to use any of these two methods, I don't need to copy and paste these functions into my code. All I need is to import that .py file, my calc, and then these guys are like automatically added to my code without me copying and pasting, and anytime I want I can use them. Note that in the past we have used modules so many times, right? Remember when we imported like a math module or NumPy or anything, that's exactly what we did. Sometimes we brought them and renamed them as something. Sometimes from that module, we only imported some methods or some variables. And sometimes from that, we brought everything in, we imported everything in, right? So if you have seen me using expressions like these, codes like this is when I have used some already available module, right? Whether it was NumPy, Math, SymPy, SciPy, or any of that. Those are all a collection of functions and methods and usable code. And this is extremely useful. So here I have this my calc.py, for which I need to use SymPy and Math and NumPy. And what this one does, it gives me two calculations for calculus that I have not covered in my symbolic expressions for SymPy. So I decided to do that because these two are typically useful things for calculus. And of course, the first one for dynamics too. One of them is calculating the radius of curvature of a function at a given point, and the other one is to determine whether a function has horizontal asymptote, and if it does, it returns the horizontal asymptote. Okay, so here I have these two functions that I have written and I explained them. And then when I save this whole thing as my calc.py, so now I can come to this test code, and the first thing I do, I import my calc module, and then here I'm going to test it, and you see here I'm using these two functions that are inside the calc, right, without me again copying and pasting them here. So this is an extremely useful idea, but let me briefly explain what I did in these two functions. And so here I asked the user to give me the name of a function as a function of x, a single variable function. So you can say cosine of x, x squared, whatever you want. I get it, but remember that when I get anything from an input command, it is going to be a string. But here, when I go to my module, I need to have it as a symbolic function so I can do derivatives, limits, and so on. So I need to do some conversion, which I'm going to talk about. But here I get that function as a string. Then I ask for the evaluation point for the radius of curvature, and it gives that to me, and then I convert it to float. So this x naught is a number. Then I would call my calc.radius curvature function. I pass it the function, I pass it the number, and it is going to type in for me the radius of curvature at that point. Then I will call my horizontal asymptote function, and this is going to give me the horizontal asymptotes. Okay, and if we want, we can have this print statements a little bit more informative. Instead of just typing in a number, I can say, for example, radius of curvature for, and then I say fun, or I can say for f of x equal fun, and then is, and then get that number and put it in. Okay, and here similarly I can say what? I can say horizontal asymptote for f of x equals, then here again fun, and then is, and then pass that number. So this way they are a little bit more informative. Okay, so let me first run this so you see the result, and then I explain what I did in these two functions. So here we go. Let's go ahead and run. Seems like I used too many parentheses. Yes, there is one here that I should get rid of, and probably one here. So let's do it again. Just deleted this, right? As okay, there we go. So here, let's say my function is x cubed, and then the evaluation point is 1, and you see it says the radius of curvature for this function is this much, and then the horizontal asymptote is infinity. This function does not really have a horizontal asymptote. Okay, so you see it is working just fine, and here I would like to add something extra for this function, and then say at, and then I add x naught, and then say is. Okay, so we also include the point, basically the value of the given point. So let's try another function. And you clearly see that now I have some meaningful message and some meaningful message here. So what am I doing in this code here? So here I get the string, I get the evaluation point. The first thing I do, I define my x to be a symbolic parameter, and then I use this command called simplify. This one will convert your string into a symbolic number, a symbolic expression. So convert string to symbolic. So now, and I have to define this x ahead of time. So when it says cosine of x or x squared, this guy, if you don't define x ahead of time, it says what is x in the cosine of x. Then the radius of curvature, as you know, is 1 plus f prime squared, the whole thing to the power 3/2 or 1.5, divided by absolute value of f double prime at the point. So here you see that I have used the subs command, and in the numerator of that radius of curvature, because radius of curvature is a ratio formula, in this guy I have plugged in x naught for x, and then for the denominator I plugged in the denominator in this f double prime x for x naught, and then I use the math absolute value function to get the denominator, and then rho is the ratio of the two, which I have returned. And for horizontal asymptote, again, I converted my string into f, and then here I assume that I have a horizontal asymptote, a finite number. Then I use the limit command as x goes to infinity, and I get this answer. Now this answer could be infinity or not infinity. So here I say if that answer is equal to infinity, make it false, which means, hey, what? This guy does not have a thing, and then since it doesn't have, go ahead and what? The value return is the numpy infinity. Else, go ahead and convert that answer into decimals. Because remember, this answer is not always decimal. It could be a symbolic expression. Convert it to decimals with 3 decimals, convert it to a float with 3 decimals, and then return that. And here, since I don't want to say yes or no, if I want, I can get rid of this true and false here, right? Because I don't have to say that. So if I want to make my code more efficient, I can even get rid of this portion. And here, let's run it one more time. So we make sure that it is working. Every time you update your code, run it again. Make sure it's working. Just because you change something, it doesn't mean you didn't make a mistake. Okay, and you see that it is working. Okay, so always check your code for potential mistakes that during the update you might have basically caused for the code. So hopefully you have some idea about a module, how to write a module, which is basically a .py code, how to import it, and how to use it. So hopefully this video is useful to you, and I'll see you in my next lecture. Thank you.